Okay, welcome and good morning, everyone. This is the 32nd edition of Soup and Science. My name is Axel Handemer. I'm the Associate Dean Academic of the Faculty of Science. And well, before we begin with our exciting science for today, I would like first to acknowledge that McGill University is on land which long served as a site of meeting and exchange amongst indigenous people, including the Anishinaabe and Haudenosaunee nations. We acknowledge and thank the diverse indigenous people whose footsteps have marked this territory on which peoples of the world now gather. Okay, and so now we are ready for our today's presentations. We will have four exciting speakers. The first one will be Professor Kartik Agarwal of the Department of Physics, followed by Professor Parisa Arya from the Department of Chemistry and Atmospheric and Oceanic Sciences. Then Professor Oliver Coombs from the Department of Geography, Professor Vincent van Hinsberg from the Department of Earth and Planetary Sciences. And we also have a student presenter today, Kei-John Wang from the Department of Geography and Earth and Planetary Sciences. So, and there's one more announcement to make just in case you haven't followed our last few presentations, Soup and Science presentations this week. At the end of the presentations, so the students will have the opportunity to answer a skill testing question about each presentation. And the top 10 students who answer the question correctly in the fastest time will win a prize. And that prize happens to be a $25 credit on your student card towards the purchase of a meal at any on-campus dining location. So, and after this 1 minute break that we will reserve for that, there will be breakout rooms where you can ask moderated questions. So it's a moderated question and answer session with one speaker and a moderator in each breakout room. You will be able to choose the breakout room you want to attend. You can actually also attend more than one if you wish. That's completely up to you. And a few minutes before noon, we will return to the main session, and there will be final remarks today by Principal Suzanne Fortier. So, and now we are ready to begin. And our first presenter will be Professor Kartik Agarwal.
Right, just share my screen. All right, well, thanks first of all to the organizers for organizing this very nice initiative. So my name is Kartik and I'm from the Department of Physics. And I'm going to be talking about quantum computing with my Ranas today. All right, so first of all, why quantum computing? So simply put, quantum computers really have the potential to revolutionize computing as we have it now. Just to give a very simple example from data encryption, if you want to factorize, say, a 17-digit number into its constituent primes, if you take even the best classical computer that we have, that would take about the age of the universe. But if you could build a decent quantum computer, it could just be done in a few hours. So the reason that quantum computers get this speed up to solve certain problems is because instead of operating on classical bits, which just take the values 0 or 1, a quantum bit can actually take the value of 0 and 1 simultaneously. In fact, it's in a superposition of being, some probability 0 and some probability 1 at the same time. And it is precisely this kind of parallel processing power where, a quantum computer can churn through all these bit strings all at the same time that gives it a speed up in solving certain problems. But precisely for this reason that it gets its advantage, it also has the following disadvantage, that it's very, very hard to isolate quantum bits or qubits from the environment, and which makes them error prone. So in particular, since you have this whole set of states anywhere between 0 and 1, a small deflection, small error can accumulate over time and give you therefore garbage results. The other thing is that it turns out error correction is much harder in the quantum setting than in the classical setting. So for these reasons, you really want to find a way of building a qubit that is very much protected from environmental noise. Now, one way of doing it is through Majoranas. And so what are Majoranas? Well, Majoranas are particle-like objects that are their own antiparticles. So if you take two Majoranas and bring them close, they annihilate each other. Do they exist in nature? Well, we don't know, we're not sure. But you can certainly find certain materials in which electrons interact very, very strongly with one another. And the result is you get Majoranas. So just to give an example of where this could happen, this is a setting in which a lot of people have invested money and energy into exploring. You have a superconductor on which you put a semiconducting wire, and if you apply the right magnetic field, it turns out you can get two Majoranas at the ends of the semiconducting wire. So why do we want to use Majoranas to build qubits? Well, one reason is that they store quantum information very non-locally. So these Majoranas are holding this information throughout the wire. And as it turns out, any local noise doesn't disturb the state of the qubit. The second advantage is that Majoranas are non-abelian. So if you just take two Majoranas and exchange them, even without ever bringing them close together, they can take a qubit and say, convert it from state 0 to state 0 plus 1. And that also, again, without invoking errors. So what they do is they implement error protection at the hardware level. Now, of course, this is a very exciting field. And for the past 10 years, there's been a lot of development, but we still haven't been able to build a Majorana qubit. And there are some important reasons that we're always trying to figure out how to fix. And so I have a lot of very nice people working on this problem with me, but I just want to mention that two of these people actually came through a Soup in Science initiative. So I'm really happy if you write to me and we can discuss in more detail in the breakout room. All right, thanks.
Thank you very much for this fascinating talk. Our next speaker will be Professor Parisa Arya from the Department of Chemistry and the Department of Atmospheric and Oceanic Sciences.
Good morning, and it's delighted to be with you today. What I'm going to be talking to you today is regarding the particles in air that is called aerosols and their impacts in health and climate. I'd like to thank my students and funding agencies and start with talking about why aerosols are important. Aerosols are the top priority of the World Health Organization. They can cause cancer, and they are known as for respiratory diseases and so forth. And also they are the highest uncertain part of research in all domains of climate change. The top, not the second, not the third. And they can be, many of them can be natural particles, and as many of them are anthropogenic. For example, nanoparticles that are emitted by industries and transport and so forth that are very common. One thing that you have to keep in mind in climate change is that greenhouse gases are not the sole forcers for climate change. The latest result indicate there are about 55% is driven by climate change, but 45% is driven by other issues, and notably aerosols. So aerosols are climate forcers, they are the uncertainty, and they can be the health hazard. How health hazards they can be, they are actually number one priority of the World Health Organization and are responsible for several millions of premature deaths every year. One thing that you have to keep in mind, because they are airborne aerosols, you already can also be biological, such as SARS-CoV-2 that I will be looking at it today. In our labs, we have established observation from remote sensing to in-ground. We do actually quite a bit of theoretical and computational chemistry that are related to the atmosphere and atmospheric interfaces. We do a significant amount of the looking at laboratory experiments and develop technology that several of them are patented. So in general, we have fundamental work to understand how the gases become particles, how radicals can change them, what happens to their surface microphysics, as well as emerging contaminants, and how we can actually make the technology much more sustainable, and also the smart sensors that are nanosensors in air that we can actually remote control it by cell phones. So we have lots of toys, and thankfully we got awarded to do other toys. But the reason we use these toys is to provide complementary information, because the challenges related to aerosol are identified to be physical chemical processes, and our laboratory addressed them and some more. I promised you I can provide you with the SARS-CoV-2. Here is, I'm so proud of it, and my graduate student and I worked on it for a year and a half. Here are in situ and real-time measurement of an observation and quantification of the activated SARS-CoV-2. And we do with other viruses and by what are aerosol at the same time. Again, when you are getting COVID-19, you're exposed through respiratory system. The aerosols and particles that are reaching you, they are airborne particle and is defined as aerosols. Besides that, we developed recently another technology for micro and nanoplastic measurement to picogram levels, which is 2 orders of magnitude to more than what it was before. And actually using the same laser that I just showed you for SARS-CoV-2, we can actually see those particles as well, but it is a very high-risk project and we have to work on it. So take-home messages: aerosols play key role in climate and health, and I love to see you afterwards.
Okay, thank you very much for this talk. Our next speaker is Professor Oliver Coombs of the Department of Geography.
Right. Well, good morning, everyone, and thanks to the Faculty of Science and credit to organize this session today. So I'm in the Department of Geography, and I work in the Latin America mostly, and I look at the nexus or the connection between environment, development, and poverty, which would be this intersection right here in what we call neotropical forests. So the area that I work in primarily is the Amazon basin, and the Amazon basin, you know, is a threatened ecosystem. The red here is the deforestation fronts that are sort of munching in on the sides of the basin. And of course, this is a concern in many respects: biodiversity, climate regulation, the availability of forest resources, and also indigenous people in the area. And these deforestation frontiers are really being driven by colonists. But there's a whole bunch of people in here who don't actually cause a lot of deforestation. They're indigenous people and they are folk people. And they live along the rivers of these various tributaries in the Amazon itself. They are considered to have deep local ecological knowledge. They practice traditional agricultural and forest harvesting activities. And they're considered to be sort of our partners in conservation and sustainability. In other words, the sort of guardians of the forest. What we don't know about these people is how they make a living, which sounds kind of incredible, but there's lots of sort of ideas out there, but not a lot of empirical work's been done. So I've been working in the Western Amazon, in Peru mostly, and looking at small communities and how they interact with their environment until about 5 years ago, when we decided to scale up and do what now is the largest household and community survey ever done in the Amazon basin, where we've contacted over 900 communities and 4,000 households to try to understand how people's livelihoods influence conservation and poverty. And this is work that I'm doing with Yoshito Takasaki at the University of Tokyo and Christian Abizaid at the University of Toronto. So what have we found? Well, we've found a whole bunch of really interesting things. We found Incan bronze axes in the jungle. We found geothermal rivers that can boil eggs. But with respect to livelihoods, what we found is, I think, I've picked out 3 findings that I sort of capture what I think our discoveries have been. And these discoveries challenge the way we think about forest people and their relationship with the environment. The first myth that I think is challenged by our findings is that forest people kind of do a little bit of everything. And it turns out, in fact, there are very few pure subsistence people left in the Amazon anymore, that everybody's got some type of relationship with the market. And they often specialize, like this guy specializes in arowana, a particular type of fish. This guy specializes in flowers for a cemetery. And this guy, avocado. And these guys over here are heavy-duty fishermen. So what we find then is that forest people are actually market specialists. Why does that matter? Well, it matters because if you're a conservation group and you're going in to talk to the folks about, I don't know, protecting monkeys or something, you'll be talking to an empty room. It might be one hunter, but everybody else is not really involved. So there's a lot of heterogeneity in how people make a living in the Amazon. The second myth that our findings are challenging is this idea that traditional forest use is fundamentally and necessarily sustainable. We'd like to think it is, but actually there's enormous variability in how people use their resources. And we find in separating what is more sustainable use from less sustainable use, that a whole bunch of factors, the type of product, who the harvester is, what the harvester's circumstances and so on, are all important. And what it means in the bigger picture is that if we're going to advance conservation and development in the Amazon basin, we really need to know the micro-foundational logic of resource use. So sustainability of forest use is really contingent. The third myth that we challenge is this idea of the imprint on the land is limited. Yeah, okay, this is not deforestation on the frontier, massive cutting of forests replaced by soy or pasture, but this is, people still have a pretty big effect on the land. And so in this case, you'll see a kind of halo around a community or many communities where the forest, the primary forest is lost, but secondary forest is preserved. In another study we've done, we looked at local ecological knowledge to look at the availability of wild resources. And what we find is that around communities close to major cities, you see depopulation, defaunation of key species like peccaries or monkeys or arapaima or mahogany trees. So yeah, perhaps the most striking is this case that a PhD student of mine discovered, which was, this is the Ucayali River. It's one of the biggest rivers in the Amazon, indeed in perhaps the world. And he discovered that it changed course, right? And created a 70-kilometer oxbow lake. And this was really intriguing, right? These rivers move around a lot. They're incredibly dynamic. But this was unusual because it went from this meander neck, in other words, this little channel here in the box, went from looking like this to looking like this, right? And he started poking around, and what he found was that it was actually caused by a group of guys, not these guys, but a group of guys with shovels and with machetes and axes. And they saw this meander neck, and they were tired of canoeing 70 kilometers around. And what they did is they cleared it each year a little bit more so the river would come through at the flood a little bit more efficiently. And then one day, they created one of the biggest cutoffs in the Amazon. What this means is that traditional practices, although we like to think that, they're, have really little effect, people with very simple technology can have a profound effect on their environment. And this applies not just today, but probably in prehistory, with people using very simple technology, could have changed not only the nature of forests, but even the direction and nature of rivers in the Amazon basin. So just to conclude, our work focuses on understanding livelihoods. This is important because these new insights we're getting are helping NGOs and policymakers work more effectively with allies that are seeking to protect the rainforest. Our future work that we're beginning now, based on the data we've been gathering, is looking more at rural poverty and the idea of spatial poverty traps. Thanks very much.
Much for this talk. Well, now we are coming to our last speaker of the day. The speaker is Kejuan Wang. He's a student in the Department of Geography and Earth and Planetary Sciences.
Right. Can you guys hear me?
We can.
Good. All right, let's start my presentation. Can you all see my screen?
Yes, we can.
Good. From beginning. All right. Hi, everyone. My name is Kejuan Wang. You can call me Kai. I'm my third year in honors major in geography, having a minor in EPS, although I'm taking more class in EPS. So I'll be talking about peat, and it's my second research as McGill. So, peatland in Canada. Well, peatland is very important globally speaking. It contains twice the amount of carbon compared to forest. And Canada is covered a lot by peatland. You can see from this diagram here. Right. So an undisturbed natural peatland would look something like this. Pretty sure lots of people have seen it before because it's very prevalent in Quebec and throughout Canada. However, the peatland I was working on looks nothing like that. It looks something like this. So it's actually harvesting peatland by the industry. They remove all the surface vegetation, they drain the peatland, let it dry, sit on the surface, and eventually they harvest them. Peat is a very good growing medium and sells very well. And fun fact, the biggest use of peat in Canada right now is actually to grow marijuana. So my research goal is to investigate the effect of management, how the industry people working, and the result in carbon emissions from drained peatland with a focus on methane on those stockpiles. So those are the two photos of my colleague working on a stockpile, doing temperature measurements and recording data. And some photos of Professor Nigel Roulet, Professor Ian Strachan, my supervisors, and me. I think I was digging a well and trying to get the gauge of the groundwater measurements. And this instrument right here is a flux tower, which has nothing to do with my measurement, by the way. It's just an instrument we installed in this harvested peatland for a while, and we can get continuous measurements of the temperature, the flux measurement of methane, CO2, water vapor, and wind directions, etc. So, how are stockpiles created in a harvesting peatland? Let's take a look at the video. Well, essentially, it's just a vacuum peat harvester, which suck up a lot of peat and dump it at a specific location in the peatland field. And we're interested in those stockpiles because they can heat up. Self-heating mechanism due to it's under its own weight, and also the decomposition of organic matter, the peat can release heat inside. There are two kinds of stockpiles, whether they're covered by this white tarp, sometimes they are black, or uncovered, totally exposed to the atmosphere. And we're making measurements of its methane emission, carbon dioxide emission, and temperature. We're interested in the temperature and methane emission because, well, as perceptive scientists, greenhouse gases, all right? Well, the industry people also want to know about it because heating in the peat can degrade the quality and then don't sell as well. So there are two important lessons I learned from my fieldwork. And number one is things can get dirty, really dirty. That's for my friend, Sophie. After an entire day of working on the peatland, it's usually how it goes. And the things can go wrong. In fieldwork, things can always go wrong. There's no escape. This is my friend, Steffi, fixing wires of our instrument while we're just waiting, sitting on top of stockpile. And yeah, that's pretty much it. Stop. I'd like to use the remainder of my time to talk about how to get involved in research as an undergraduate student and with my background as an international student, because I find it difficult sometimes for international students like me to reach out. I know I feel shy. I feel shy to talk to the prof. I feel shy to reach out to opportunities, but I strongly encourage people of reaching out to prof and just send an email or to go to their office or to go to events like Super Science. My next slide is dedicated to Professor Bernhard Lenner, whom I went to the Super Science session 2 years ago and talked to him after his presentation. I sent my email afterwards, didn't get it back for 2 months. I said, okay, this is dead. Okay, fine, I'll forget about it. But at the end of the semester, he actually get back to me with an offer. Would you like to work worked with me in the summer for SURA project. So SURA is a Science Undergrad Research Award that's available for both international students and local students. So that's how I started with my research. So big shout out to Bernhard Lanner. Without him, I couldn't have started my research experience at McGill. And that's it. Thank you.